In this lecture, we will start looking at mass and energy conservation equations in a general 3-dimensional coordinate system, where the concentration and temperature fields, for example, vary in all 3 coordinate directions and in time. We will consider these equations in different coordinate systems, okay, in what are called orthogonal coordinate systems. An orthogonal coordinate system is one where the coordinate directions are perpendicular to each other at all points in space. Okay. The coordinate directions could be a function of position, but at each position the 3 coordinate directions are perpendicular to each other. Okay. Examples of orthogonal systems are the Cartesian, the spherical and the cylindrical that we had considered. In spherical and cylindrical coordinates, for example, the radius vector, the radial coordinate, okay, is the direction of the radial coordinate is a function of position around the axis or around the center. Okay. However, at each point all 3 coordinates are perpendicular to each other. So, we will first derive equations in specific coordinate systems, specifically the Cartesian and the spherical coordinate system. And I will later express these equations in terms of vector notation. The vector notation, the vector operators that we will use are general. They apply to different coordinate systems. The equations have the same form when they are expressed in terms of vector operators, but these vector operators have different forms in different coordinate systems. So, we will first derive it in specific coordinate systems, and then I will tell you, then I will motivate the form of the equation in terms of vector operators. So, first is a Cartesian. Three axes, all perpendicular to each other. Okay. X axis is out of the plane, y and z are in the plane. This is a right-handed coordinate system. Okay. And within this, each location is defined by 3 variables x, y and z. Okay. Each location is specified by 3 variables x, y and z. Okay. And at each location, okay, the 3 unit vectors are Ex, Ey and Ez. Okay. Okay, they have unit magnitude and direction along the coordinate direction. Okay. Ez. Okay. And since they are orthogonal to each other, that means that Ex dot Ey is equal to Ex dot Ez is equal to Ey dot Ez. That has to be equal to 0. Okay. Recall that the dot product of 2 vectors is A dotted with B is equal to the magnitude of A, the magnitude of B times cos of the angle between the 2. Okay. When the angle between the 2 is pi by 2, that is, they are perpendicular to each other, that cos is 0, and therefore, the dot product of 2 unit vectors, 2 different unit vectors is equal to 0. The dot product of the same unit vector with itself, okay, has to be equal to 1. it has unit magnitude. Okay. So, those are the coordinates and the unit vectors for a Cartesian coordinate system. Now, how do we derive the conservation equation in this 3-dimensional coordinate system? The procedure is exactly the same as what we had derived for a unidirectional flow. We consider a differential volume, okay, differential volume whose surfaces are surfaces of constant coordinate. Okay. So, around this location x, y, z, a differential volume whose surfaces are surfaces of constant coordinate. Okay. That means that there are two surfaces perpendicular to the x direction, that is the front and the rear surfaces, two surfaces perpendicular to the y direction, that is the right and the left surfaces, and two surfaces perpendicular to the z direction, that is the top and bottom surfaces. Okay. So, if I expand this out, this differential volume here, okay, okay. The two surfaces perpendicular to the x direction are the front surface, in which the unit vector is in the plus Ex direction, the rear surface where the unit vector is in the minus Ex direction. Okay. The outward unit vector, okay, on the front surface the outward unit vector is in the plus Ex direction, on the rear surface the outward unit vector is in the minus Ex direction. On the right surface the outward unit vector is in the Ey direction, on the left surface it is in the minus Ey direction. At the top surface the outward unit vector is in the plus Ez direction, on the bottom surface it is in the minus Ez direction. So, these are the surfaces of the differential volume. Okay. And okay, so the 6 surfaces are, okay, the rear surface at the location x. Okay, so the dimension in the 3 coordinate directions, I will assume they are delta x in the x direction, delta y in the y direction, and delta z in the z direction. Okay, so this delta y is not there. Okay. Okay. Delta y left to right, delta x rear to front, and delta z top to bottom. Those are the dimensions. Okay. So, the rear surface is at x minus delta x by 2. Okay. The unit vector perpendicular to the surface is Ex. Okay. It is actually is Ex, this is perpendicular to the Ex direction. Okay. And the surface area is delta y delta z. Okay. At the rear surface, the surface area is the increment in the y direction times the increment in the z direction, delta y delta z. The front is at x plus delta x by 2. Okay. It is perpendicular to the Ex coordinate once again, and the surface area is the same. Okay. And then there is the left. The surface area is delta x delta z. The right at y plus delta y by 2 is perpendicular to the y coordinate, and the surface area is delta x delta z. Okay. And then there is the bottom, okay, z minus delta z by 2. Okay. Ez is perpendicular to the z direction, the bottom surface. Surface area is delta x delta y, and the top, it is at the location z plus delta z by 2, and Ez is perpendicular to Ez, and it is delta x delta y. Okay. So, these are the 6 phases. Balance equation. Okay. The balance equation is that for mass, for example, change in time delta t is equal to mass in minus mass out plus the production. That is the conservation condition. Okay. That has to be applied for this, differential volume of sides delta y, delta x and delta z about the location x, y, z. Okay. So, the change in mass in time delta t is going to be the change in the concentration times the volume. After all, mass is equal to the concentration times the volume. Volume of this differential surface is delta x, delta y, delta z into the concentration at x, y, z, t plus delta t minus the concentration at x, y, z, t. Okay. What are the mass in and the mass out? Okay, so there is mass that is coming in at the surfaces perpendicular to the x, y and the z directions. Okay, there are masses that are coming in. The mass is equal to the component of the flux perpendicular to the surface times the surface area times the time interval. Okay. In and out is equal to the flux perpendicular, the component of the flux that is perpendicular to the surface, okay, because it is only the flux perpendicular to the surface that results in transport of mass across the surface. Component of the flux parallel to the surface does not result in transport of mass across the surface. Okay. So, the flux perpendicular to surface times the area times delta t. Okay. So, that is how we would account for the mass that is coming in and going out of the surface. Okay. And the flux consists of 2 parts. Okay. Flux consists of 2 parts. So, for example, flux in x direction, it consists of 2 parts, that is, one is the convective flux. Convective flux, you recall, is the product of the concentration and the velocity perpendicular to the surface, okay. And the diffusive flux is J, okay, the component in the x direction. Okay. So, this is the flux in the x direction. Okay. So, using these expressions, we can calculate the mass in and the mass out of the 6 phases of this volume. So, mass in at rear surface. Okay. Recall that the rear surface is at x minus delta x by 2, the rear surface is at x minus delta x by 2. Okay. and the surface area of that real surface is delta y delta z. Okay. And if the flux is in the plus x direction, that means that the mass is entering at the rear surface. Okay. If the flux is in the plus x direction, mass is entering the rear surface. So, mass in at the rear surface is going to be equal to C Vx plus Jx at the location x minus delta x by 2, okay, into the surface area delta y delta z into delta t. Okay. For the front surface, which is at the location x plus delta x by 2, okay, for the front surface which is at this location x plus delta x by 2, a positive value of the flux means that the flux is in the positive x direction. That means that the flux is leaving the volume at the front face. Okay. At the rear face, if it is in the positive x direction, it is entering the volume. At the front face, if it is in the positive x direction, it is leaving the volume. Okay. So, mass out at front surface is equal to C Vx plus Jx at x plus delta x by 2 into delta y delta z delta t. Okay. Those are the front and rear surfaces. Okay. Then mass in at the left surface. Okay. At the left surface, you can see that if the flux is in the plus y direction, then mass is entering at the left surface, if the flux is in the plus y direction. Okay. So, mass entering at the left surface is going to be equal to the flux perpendicular to the surface C Vy plus Jy at y minus delta y by 2 into the surface area. Surface area of the left surface is delta x delta z. Okay. Surface area of the left surface is delta x delta z. Okay. And then on the right surface, there is mass going out. Okay. At the right surface, if the flux is in the plus y direction, then the mass is leaving the surface. Okay. At the right surface, if the flux is in the plus y direction, the mass is leaving the surface. So, this gives you the mass leaving the surface at y plus delta y by 2. Okay. So, and this is equal to into delta x delta z. Okay. So, those are the left and right, and then there is the bottom and top. Okay. Mass in at bottom is equal to C Vz plus Jz at z minus delta z by 2 into delta x delta y. Okay. If the flux is in the plus z direction at the bottom surface, okay, that means that there is mass entering this volume. Okay. And if there is a flux in the plus z direction at the top surface, that means that the mass is leaving. Okay. And the surface area of the top and bottom surfaces are delta y into delta x. Okay. So, So, those are the masses that are entering and leaving at the 6 phases, and the rate of production of mass can be written as S times S is the rate of production per unit volume per unit time. Okay, production due to reaction, for example, is the rate of production per unit volume per unit time multiplied by volume multiplied by time. Okay. Okay. So, those are the terms in this balance equation. Okay. So, those are the terms in this balance equation. Okay. Those are the terms in this balance equation. Putting it all together, okay, on the left side is the rate of change, okay, that is delta x, delta y, delta z, that is the volume into C at x, y, z, t plus delta t minus C at x, y, z, t. Okay. That is equal to net flux left and right phases. Okay. Flux coming in on the left phase is C Vx plus Jx at x minus delta x by 2, that is coming in at the rear phase, minus C Vx plus Jx, that is what is leaving at the front phase. Okay. Whole into the surface area, okay, delta x, I am sorry, the left and right phases have surface area delta y, delta z into delta t. Okay. That is for the front and rear faces perpendicular to the x axis, the surface areas delta y and delta z. Okay. Plus the left and right C Vy plus Jy coming in at y minus delta y by 2 minus what is leaving at y plus delta y by 2 times the surface area perpendicular to the y axis is delta x, delta z, delta t, okay, plus the top and bottom. Okay. Bottom what is coming in is C Vz plus Jz at z minus delta z by 2 minus C Vz plus Jz at z plus delta z by 2, leaving at the top, into surface area perpendicular to the z direction is delta x, delta y and delta t, okay, plus the rate of production of mass, okay, plus S delta x, delta y, delta z, delta t. Okay. That is the balance condition. Divide by volume, divide by time. Okay. Take the balance condition, divide by volume, divide by time. Okay. And on the left side, if I divide by volume and divide by delta t, I will get C at x, y, z, t plus delta t minus C at x, y, z and t by delta t. That is the left side. Okay. On the right side, I will get C Vx plus Jx at x minus delta x by 2, okay, minus C Vx plus Jx at x plus delta x by 2, the whole thing divided by delta x. Okay. When I divide by volume and by delta t, right, delta t cancels out, delta y and delta z cancels out, and in the denominator I will have only delta x, okay, plus in the y direction. Okay. the whole thing divided by delta y, okay, plus the z direction. The whole thing divided by delta z plus the source, because here I have source multiplied by volume and time. So, that just becomes equal to the source. Okay. And now you take the limit delta x, delta y, delta z, delta t going to 0. Okay. Take that limit. Left side is just partial c by partial t. Okay. On the right side, I have partial by partial x of c vx plus jx, okay, with a negative sign, because c vx plus jx is the value at x plus delta x by 2 minus the value at x minus delta x by 2 divided by delta x. Okay. Here I have the negative of that. Okay. I have the value of x minus delta x by 2, okay, minus the value at x plus delta x by 2 divided by delta x. So, it is the negative of the derivative. Okay. And similarly, this will be minus partial by partial y of c vy plus jy minus partial by partial z of c vz plus jz. Plus s. Okay. So, that is the total equation. Traditionally, this equation is written by taking the convective terms to the left side. Okay. So, I will get partial c by partial t plus partial by partial x of c vx plus partial by partial y of c vy plus partial by partial z of c vz is equal to minus partial jx plus s. Okay, so, that is the momentum conservation equation. Constitutive relation, okay, we know that jz is equal to minus d partial c by partial z. This is Fick's law for diffusion. Similarly, for the other components, jx is equal to minus d partial c by partial x, jy is equal to minus d partial c by partial y, where d is the diffusion coefficient. Okay. So, substituting that in here, you get partial c by partial t is equal to d by dx of jx, which is d times partial c by partial x, okay, plus d by dy of jy, which is minus d partial c by partial y. Note that there is a negative sign on the right side and a negative sign in the expression for the flux. So, if you multiply the two, you will get a positive sign. Okay. That is the conservation equation. If d is independent of position, then you will get partial c by partial t plus is equal to, you can take the diffusion coefficient outside and you will get partial square C So, these are the different forms of the mass conservation equation in a 3-dimensional Cartesian coordinate system. Okay. These are the forms of the mass conservation equation, the convective parts on the left and the diffusive parts on the right in a 3-dimensional Cartesian coordinate system. We will examine this in some more detail, express it in terms of vector differential operators and try to interpret these relations in the next lecture. I will continue this derivation of the conservation equations in the next lecture. I will discuss a little more about Cartesian coordinate system before we go on to a curvilinear coordinate system, that is the spherical coordinate system. I will continue this in the next lecture. I will see you then.